This very short lesson is going to be on some of the key points of one-to-one function. So remember, this is from our very first lesson when we were first starting to talk about inverses, the definition of one-to-one. A function is one-to-one if no two inputs correspond to the same output. The easiest way to conceptualize this is by looking at the graph of a function. So we're going to look at a graph and we're going to ask the question, is this function one-to-one? So I'm sure you will not be surprised to hear that we're going to look at more than one example. So here's an example of a function. I'm going to draw my axes. Okay, and then here is my function. And what you see here is that this output right here, let's just call it A. Well, okay, well f of 0 is A, which is fine. But whatever this is, that input corresponds to the input A, and so does this one. So here we see three different inputs correspond to the output A. So this is not a one-to-one function. On the other hand, let's look at another example. Oops. So here's an example of a function. Okay. So this function, if I pick any output at all, so remember again, outputs live on the y-axis. So I'm picking this one for no particular reason. Let's call it something, we can call it A. It doesn't matter. If you look side to side, if you kind of scan around this way, that way, what you'll notice is there isn't more than one input. So if you kind of dot out a horizontal line, there it is. There is the input that corresponds to the input A, but there isn't another one. So, of course, as long as we presume that the function continues on in this way, and we always do, at least for our purposes, presume that whatever we see on the graph is what we get. So this function, we can say no two inputs correspond to the same output. So this one is one-to-one. What we are seeing here is something that will also be referred to as the horizontal line rule, which states that as long as no horizontal line crosses the graph of the function in more than one place, it is called a one-to-one function. Okay? Another approach uses the second half of the definition. So you can see here that in the definition I said a function is one-to-one if no two inputs correspond to the same output. And then underneath I said this means f of A is equal to f of B if and only if A is equal to B. So say you have a function, I don't know, f of x is equal to 3 over 2 minus x. And someone asks you, is this one-to-one? And for whatever reason, you either don't have time or you don't feel like looking at the graph. So let's look at f of A. Right, so we all know how to do f of A. That's like our lesson from average rate of change. So f of A is 3 over 2 minus A. F of B is 3 over 2 minus b. So we are looking at the output that this function assigns to the input a and the input b. And what we want to see is it possible for these two to be equal to each other without a equaling to b? Is there any situation where a is not equal to b, but the outputs are the same? Well, let's set them equal to each other and see what happens. So again, the question is, can this happen for a not equal to b? Generally speaking, when we have equations with denominators like this, we clear the denominators out. So we're going to multiply both sides by the product of the denominators so that they both clear out. On the left, we're left with 3 times 2 minus b, because the 2 minus a's reduce. On the right, we're left with 3 times 2 minus a, because the 2 minus b's reduce. And so we have distributing 6 minus 3b is equal to 6 minus 3a. And what I hope you all see here is, at this point, I can subtract off the 6's from both sides. So they will reduce off. So what this means is negative 3b it must be equal to negative 3a. And again, at this point, I can divide both sides by negative 3. And so what that means is b must be equal to a. In other words, the only way for f of a and f of b to be the same is if b is equal to a. So what we see here is, yes, we can write it in pretty color. Yes, f of x is 1-to-1. You will sometimes come across examples of functions where you know enough about the shape of its graph that you're visualizing the graph and you can see, you know what, that graph is going to cross any horizontal line more than once. So one really, really dynamic example of that, I hope, is parabolas, right? We've worked with parabolas a fair amount. We're actually going to work with them more this week. And I think by now you're pretty comfortable with saying that if I give you a quadratic function, right, whatever. In fact, let's not make it plus 1. That almost feels too easy. Let's make it like plus, I don't know, 7. You know in your head, well, the graph of this thing, this is a quadratic function. The graph is going to be a parabola. So this is not a 1-to-1 function. So you know that. But let's say someone says to you, show that this function isn't 1-to-1 without using the graph. For whatever reason. That's just a constraint that someone puts on us. So all it takes one output to match to more than one input. And as you all know, if a quadratic equation has any real solution, it has a second real solution too, right? So we're going to take x squared minus 2x plus 7, and we're going to set it to any number at all. Now, to save us time, I'm purposefully going to set it to a number that's bigger than 7, and you'll see why. So I'll pick 10, okay? If you pick a number that's smaller than 7, what you'll see is that equation doesn't have any real solutions, but it doesn't matter if one equation doesn't work. As long as we find one where there are two values of x that makes that happen, it's not 1-to-1, okay? So we'll subtract 7 from both sides, 10 from both sides. So this works out really well. This factors. So we have x minus 3 times x plus 1 is equal to 0. So this happens when x is 3 and when x is negative 1. So what we see here is f of 3 is equal to 10 and f of negative 1 is equal to 10. So there are two different inputs that match to the same output. So this function is not one-to-one. So if you ever need to show that something is not one-to-one, it's actually almost easier to just find one output that matches to more than one input. And as long as there's one place where the horizontal line crosses the graph in more than one spot, the function is not one-to-one. So looking ahead a little bit, and this is going to be something that we pick up in the next lesson, you might be thinking to yourselves, well, then how on earth are we going to talk about functions that aren't one-to-one and their inverses, right? Like that seems like it's going to be a problem because it seems like a lot of functions are not one-to-one. So that's something we'll talk about in the next lesson. And for now, that's all I got for you. Bye.